Okay, hey everybody, good morning. Thanks for joining this session of nTop Live. I'm Blake Johnson. I'm a customer success engineer at nTopology. I'm going to be talking about parametric design and how we can kind of bake into our nTop file like some fundamental equations that are used to define rocket nozzle geometry. And if you have questions, you should be able to ask them in the Q&A, and I'll try to keep track of them and pause for questions. And if you want to go ahead and try to ask, I'll see if I can see it, or just wait for the end, and we'll do Q&A at the end as well. So I want to talk about some tools that I think are really cool from the, let's go over here, from kind of hobbyists and educators and professors. They'll often make, this is like a really simple example, but they'll often make visual kind of widgets or applets that demonstrate stuff that's physical in a way that lets you kind of play around and move things and understand concepts. And for instance, like here's one for a magnetic field. Here's one for waves in a lens, or like light waves in a lens. You probably remember these from physics class, sine wave stuff like that, where I can really play around with things, and all of the physical equations and the physics of all this stuff is baked into these little pieces of software, and it's nice because you can look at visually what's going on and create 3D things. And these are really simple examples, but we also have some more complicated ones. For instance, this is one for designing a rocket nozzle, and credit to the creator of that, which is, hold on one second, let me get rid of that. From Virginia Tech, it looks like, let's see, who is the creator? Well, you can Google convergent divergent nozzle tool, and this is a really cool object or little app, because what I can do is design a nozzle, move things around, and here look at the area ratio and get physical things about what the gas would behave like in the nozzle. So now I have a temperature distribution. Now I have a pressure distribution along the distance of the nozzle, and here's the speed. And these kind of things are really powerful, but when you go into actually design a physical part, you then have to kind of take what you learned from this and then design your part. And maybe you can try to copy and paste some data, but there's nothing kind of fundamentally baked in about the physics connecting to the physical part. And so, these little tools, we can build things like these in nTop, right? We can build in the physics into nTop notebooks, because we can import data. We can do a lot of complicated math operations. We can do exponentials and sines and any kind of large scale vector calculations. And so we're going to do a quick example that allows us to do something similar to this. Like, let's say we have one of these inputs. Let's say maybe it's the profile of the speed of the air in the rocket nozzle as you go along the distance of the nozzle. And then if I do that, then what does everything else look like? Because all these things are connected, right? The pressure is connected to the speed, the temperature is connected, the geometry is connected. And so I'm going to go over to nTop, and we're going to talk about that. So here we have, let me just quit there. Here we have the nTop file, and I'm going to go through it together, or we're going to go through it together. First, let's talk about kind of what's coming in to the data. So what I have is this is the only thing that's really driving the geometry. And what this is a relationship that I have been I'm striving for the speed of the nozzle along the distance of it. When I say speed of the nozzle, I mean the speed of the gas flowing through the nozzle. So I want it to, start small and get high, because that's what a nozzle does. And I want that to happen over this distance of the nozzle, which I've normalized to be 0 to 1. So you would multiply this by like whatever the length of the nozzle is to get something like 10. Or whatever that would be, right? And a lot of this is taken from Richard Naka, who I believe works with the same people that made that little app we showed. And he has a really good website explaining what nozzle theory is and the assumptions that we make about the physics and the thermodynamics, and what nozzles are designed for to get as high of an exit velocity as possible. And I agree with him in saying, it's really an elegant simplicity, an example of that, because what you have is a goal of just going from high speed, or lower speed to high speed, and somehow we get this nice bell shape. So what's actually happening there? Well, combustion is happening here, and on this side you have subsonic flow, and on this side you have supersonic flow. So this is called the throat, and that's where your Mach is equal to 1, M-A-C-H. So that means that you're at the speed of sound. And so you come in slower, you reach the speed of sound here, and you increase speed as you go throughout. And I'm not going to go through all the thermodynamics and all the physics, but there's a lot very clearly explained here. And the takeaway here is that we have this relationship between the area of the flow, so what's going through the nozzle, that area, and the speed that we want to deal with. And M here is the Mach number, so that's the ratio of the speed divided by the speed at the speed of sound for the gas. So if you're at Mach 1, you're going the speed of sound. If you're going Mach 2, you have twice the speed of sound, right? So it's really just a measure of speed. And so we have this relationship between area and the speed. And then we have K, which is just a constant. It's a property of the gas or whatever the fuel is that's flowing through the nozzle. And when you plot this equation, something really interesting happens, because what you get is this smiley shaped curve where in order to continually increase speed, you need to have an area that's larger that then comes down to a minimum at Mach 1, and then it starts expanding. And so that's where the elegance of this design comes in. That's where you get this bell shape that's recognizable to everybody, as a nozzle. And so what I did is built an nTop file that bakes in this equation directly into it, so that I can tell the nTop file, I'd like this speed over the length of the nozzle. So I want you to spit out a specific cross-sectional area for the gas to float through that gets me that speed profile. And so I took a typical speed profile for the nozzle, which is something that looks like this. And that's kind of just, your rocket scientist would generate this for you, right? They do all the calculations saying this is what we need, this is what the combustion will be, this is the exit velocity, all that. They give you this profile, and then they say, okay, I need a rocket nozzle. And so your job as a designer is to take this and figure out how to do that. But with nTop, you could have a rocket designer that handles a lot of this for you, right? If you understand the equations that are going on in here. And so let's look at the nTop file. And what we have here is just a line that's been expanded out and shelled. And so that's how we create this nozzle. So the line gets thickened out to a certain distance, and then we do a shell to actually create the flow path for the gas traveling through the nozzle. And as you can see, the radius at which we're expanding out this line is changing as we go along the axis of the nozzle. So let's actually get to the nitty-gritty of how we did this. If we go back to the Nozzle Designer spreadsheet I put in here, this is just, what input we have into it. So what I have is a point map, X, Y, Z, and then a value, a mock number value. And so we don't really need to move anything around in X and Y. I mean, we could, but we're just going to make this go straight up the Z axis. And so we have this increasing from 0 to 1, like a normalized distance along the axis. And then this just desired Mach number. And then I export this to a CSV. So you can just download this as a CSV, and we'll have these values in a text file. And then I can import this text file. And if you look in here, I could see I have my points, which are 0, 0, and then just increasing along Z. And I have my values. In the properties tab, we can look at the values, and those are the Mach number values. So I just drag these values out and put them here, and now I have the Mach number that we desire as we go along the axis. And we also have the points, right? So I just pulled out the points and put it here. Now remember, these points are ranging from 0 to 1, so I multiplied them by a nozzle length, and now I specified that in the inputs, so that's 10. So now if you look at our nice new ruler, you can see the nozzle is actually going to go from 0 to 10 millimeters, right? And whatever length I put in, it'll just expand it out. So then this is where we bake in the equation. So we have, from this kind of fundamental thermodynamic relationship, we have something that connects the speed, which we just inputted, to the area that we need to get that speed. And so we have this block called evaluate expression. And what that lets us do is make really complicated kind of MATLAB style or Mathematica style equations typed out. And then we just put in A and B, and that's going to represent what are kind of localized variables. So I use this Mach number here for M, in this case, A. And then for the constant, the specific heat ratio, I use B, which is defined up here as 1.4. So now we have a list of areas that we need to generate. And so you can go in here, look at the properties, and we have actual cross-sectional area that the nozzle needs to have. And then, I should say, it's not strictly an area, it's the ratio of areas, right, to the area at the Mach 1 number. So that's what A star is. It'll have some certain radius or some certain area at Mach 1, and everything else is related to that. So now we have a radius that we're going to get from the area. And that is going to be just pi r squared. That's rearranged a little bit because it's also, we're solving for some value within this equation, but it's just simple algebra, right? We have a ratio of areas. Let's just get the radius that we need all along the path of this to create those cross-sectional areas. And then we define our axis. That's just basically taking the scaled points that we have here and doing a curve through points, so that now we have this as a line. And we're just going to thicken this line. I said this earlier, but we're just going to expand this line out to a specific radius because that's going to get us the desired cross-sectional area. And so I have a thickened body block here, and I have the implicit body from curve. So just converting this data type into an implicit body and expanding it out. Now, to do this, I'm going to use a transfer function, and that may be something that you guys haven't used before, so I'm going to do a quick demo on it. Before I switch over to that, I'm just going to check for questions. Hold on one sec. I think we're okay, but I'll check the chat as well. Okay, great. So thank you for that. So we have this transfer function block. If you know the ramp block, you should be in a good position to understand the transfer function. But if you don't, that's okay. We're going to kind of start from scratch. So a transfer function block takes in a field. And let's use, for instance, this field, which is going to be We can just use 10, 0, 1, 0. This is a plane, right? So we're just going to use this field that increases along the z-axis, right? So if I probe it here, it's 3. If I probe it here, it's 0. If I probe it here, it's -3, right? Makes sense. And then what you can do with the transfer function is put reference points to drive a new field, where if I have an input value, let's say it's 0, then I can tell that tell the new field to be 1 there, and then do another reference point where I say where it's 1, make it -1, and you can put anything you want here. What I did is just do a pattern that's -1 and 1. And so if we view this, what we see here is it's just scaling back and forth between 1 and -1. And so it's piecewise ramping, right? You have a ramp from here to here, and then a ramp from here to here, and here to here. And you can really put any numbers you want in here. This is just a simple example to show you can kind of create a triangle going back and forth from 1 to -1 as you go further out. And so you can imagine I did kind of a similar thing with my transfer function in the Nozzle designer. But what I put in is the points along the axis in the z direction. So you're basically just increasing linearly, 0, 1, 2, 3, 4, 5, 6, 7 to 10. And then I'm putting in the radii at the desired radii at these points all along the way, because I know that from calculating it based on this area equation, getting the radius, and then now I'm scaling up. Excuse me, I'm scaling up the radii based on what's desired to get me this desired Mach number, right? Another just quick explainer for the transfer function, we have this extrapolation. It shouldn't matter in this example, but basically you can either expand it linearly as you go out or clamp it as you go outside of the bounds of the input. So if you're like less than 0 in this case and above 6, you can clamp it or let it linearly interpolate out in the direction it was going. Not super important here. Just wanted to, for completeness, explain that input. So now I've thickened my my line here, and you'll see that it is. It take a little while to build, so let me go to medium res. It's not going to be very pretty because the edges, the inlet and outlet have also been thickened, right? They've also, if there's a point here, it thickens in every direction. And so it's also created these little half spheres. And so we need to trim those off real quick. And so we do that with planes. So you can intersect or you can subtract planes. If they're oriented correctly, they'll just, if you look at the plane of this, 0, 1, 0, you can see it has a clear negative and positive side. So I'm just going to subtract off the one side. So that's how these are being removed. And another step we do in this block is to shell the shape. So if we look at this, it shouldn't look any different because we're shelling. But if we do a cross section, we see we've actually created a shell. And so another important thing is I used a outward shelling because that maintains the exact cross-sectional area that we have from this shape. So it's taking this and shelling outward from it, which allows us to maintain that cross-sectional area for the flow. So we can look at this, and this should be kind of our final nozzle. Let's just go back to medium res. So this is a little slow to build because of the transfer function block. It's having to do a little extra math. But here we can also just render this with high res using Control H, and it looks good pretty quickly. So let's do that again. And so that's a pretty smooth looking nozzle for basically no input, telling only really defining the length and the radius here at the throat. And another cool thing, if we go back to this page, we learn more things about the relationship between the thermodynamics and the geometry. We can go up here and we can learn that, well, if I have the Mach number and I have this specific heat ratio, which is just a constant, I can actually figure out the temperature distribution and the pressure distribution of the gas that's flowing through the nozzle. And it would be a whole lesson in its own right to explain how these are derived. It's all second law of thermodynamics and things like that. But the point is we can take this from an expert that knows about this, rocket scientist, to just bake it into our nTop file. So now I've created fields here where I can look at not only the Mach, which we inputted, right? So let me change this to jet, and we can see, okay, this is the Mach, right? It starts out small, goes to 1, and then it increases. That's the speed throughout the nozzle. We also have a pressure field, and this, again, just from these equations. And we also have a temperature field. And so that's really cool, right? It's really just multiplying and dividing and doing exponents with fields from what we take from this equation. And so if we have this pressure field, again, no simulation, nothing required, just fundamental physics, we can do something with it. So the last step, I can just take a little while to render, but I can have some ribbing that I'm going to add to the outside of the nozzle. And I'm going to use a ramp block to have that ribbing be more substantial and thicker where there's higher pressure. So I have, like I said, this ramp, which takes in the input of this pressure field. And you see, here's some higher pressure. This is where combustion and everything happens, and then there starts to be expansion. So you have lower pressure, or higher velocity, so you have lower pressure. And so we're taking this pressure field, bringing it in here, and saying wherever you have high pressure, do a higher thickness of this Voronoi ribbing, and then where you have low pressure, do lower ribbing. And that's all on this Voronoi emboss, which is one of our toolkits under, I believe, architected materials. And we can take a look at this high res. You can see here's the high pressure, so here's more ribbing, right? And again, all I did was just clean this up by subtracting out anything in our subtraction bodies list, which is, the planes here, and also the inside volume, just to make sure that we're not keeping anything. We want to keep this cross-sectional area clear. Okay, so that's kind of our final design. I'm going to let it render on highest res so we can get a nice, good look at it. And the last thing is just one more equation that we can get from the rocket scientists, right? We can get something that tells us what the actual exit velocity of the nozzle is and the pressure at the exhaust. And this again is just a function of temperature, some gas values, some gas constants, molecular weight of the exhaust gas, things that can be assumed to be constant for a simplified model like this. And when you do that, you can actually just type those equations in using, again, evaluate expression. And I generate an exhaust speed based on my my inputs and my geometry. And so I've not only built like the nozzle, like this isn't just CAD, right? We're doing more than that. We're able to visualize things that are fundamental to the physics of what's going on. We're able to get parameters out that might be useful. We're able to add ribbing to the structure based on a pressure field that we know from physics. So, and again, all of this is really open-ended. I want to emphasize that, this isn't meant to just be possible for a rocket nozzle, but for anything where you have a lot of fundamental information about what's going on. You don't have to rely on simulation. bake that into your nTop files so that a user can really just input what they want and not have to worry about doing anything else. Because now I can give this to someone who doesn't know anything about the nozzle. Or maybe I modify it so that, the inputs are a little more clear to the non-user, and I can still just build nozzles based on these fundamental physics equations. So I'll let this render and I'll check for questions again. Are these files posted anywhere? We can, yeah, we'll post all of this. I believe, I don't know what the process has been for nTop Live, but we'll make sure this is posted. Gabby, I don't know if you're on, but I think we have a process for that. And if you don't see them anywhere, you can always email me. I'll put my email address up at blakejohnson@ntopology.com. So that's my email if you ever want to reach out. And there we have the files we posted on the website with the recording of the session. So yeah. Okay, any other questions? I'm still waiting for the render, but might have to leave it with a little bit of suspense. Oh, there we go. There's our final part. And again, that surface is smooth and on the inside, and we have this ribbing that's thickened based on the pressure. So with no questions, I think I'm going to end the session. Thank you for joining, and I hope you found this informative, but also I really hope you're inspired to work more on and nTop notebooks that are like this. And the answer to this question, how to generate files from CSV file. So that's as simple as going to, you can use Excel or whatever, but this is just downloaded as a CSV. And this is just taken from a typical rocket nozzle design. This is what the Mach number would look like as you go along the distance. So this is kind of dummy data. This is what would be coming from a rocket designer, and it could also, other things could be inputted. You could input the geometry and then use that to get a Mach number result, or you could generate, you could know what the temperature profile needs to be, and vice versa for all those things. So, but yeah, the CSV is just by downloading it as a CSV, and then importing it as a point map in the first step. Okay, no more questions. So thank you guys so much, and have a great day.